Every example we've done so far of the limit comparison test worked out to be a finite number. In other words, we were always working in case 1 for example 2. But now let's take a look at these other weird things that can happen. We could have the limit be 0, we could have the limit be infinity, and some appropriate cases to go with it. All right, so let's look at that problem. Now, keep in mind, we actually know what this particular problem is. We know that this is a divergent series. So this is obviously not going to prove convergence or divergence. I'm going to show you what happens with the weird parts of that theorem. And this is a convergent series. All right, so let's take and let's suppose, and actually I'm going to divide the page up a bit. So method number 1, I'm going to let a sub n be 1 over n squared, and b sub n, I guess it doesn't really matter. I'll let a sub n be 1 over n. It doesn't make any difference. I'm going to do it both ways. So, but you guys are used to the first one being the first one. It does not have to be. It's arbitrary. And then b sub n equal 1 over n squared. Sure, why not? Okay, so if we do that, then the limit as n goes to infinity of a sub n over b sub n is the limit as n goes to infinity of 1 over n. I'm just going to write it this way. 1 over n divided by, because that's that division bar, 1 over n squared. That would be the limit as n goes to infinity of 1 over n times n squared over 1, which would be the limit as n goes to infinity of n squared over n, which is the limit as n goes to infinity of n, which is infinity. Okay. Well, okay. Think about this. This was a convergent p series in my denominator. Right? So I choose the convergent p series for the denominator. So here, right, this is the convergent, and that's the b sub n. Okay. But I got infinity, and right, the limit was infinity. So let me make this clear. So L is infinity. That's great. But then I need my denominator series, b sub n, the one I chose to be the bottom, to be divergent. But it wasn't. It was convergent. It's inconclusive. Right? The denominator series I chose, right here, denominator, right? It flipped over and became in the numerator. That's the denominator part. It's b sub n. I chose that to be my b sub n. It was convergent and infinity. This is inconclusive. I didn't prove anything. The limit comparison test did not do it for me. Boo. Right? And that was because the L was infinity, but b sub n is convergent. This was actually case 5 that I made up. L was infinity, b sub n converges. It's inconclusive. Right? So this is case 5 from the theorem. All right, well, that was useless. Now, what about the other side? Well, again, a sub n, b sub n is arbitrary, so what if I flip it and see if I can get it to go the other way? So let's try it again. Let's let, I'm going to go green here. So I'm going to take method number 2. So let's try it the other way, since this did not work out. So let's let a sub n be my numerator. Let that be 1 over n squared. And then b sub n is 1 over n. Now notice that's a divergent series. Right? We already know that. That's the harmonic series, so we know it's divergent. All right, so now let's take the limit as n goes to infinity of a sub n over b sub n, as required by the theorem. But again, which one's a and which one's b is a bit arbitrary, as long as it works out the way you want in the theorem. So this is the limit as n goes to infinity of a sub n, which is 1 over n squared, divided by 1 over n. Right? This division here is becoming that division symbol here for the sake of ease of writing. So that would be equal to the limit as n goes to infinity of 1 over n squared times n over 1, which is the limit as n goes to infinity of n over n squared, which is the limit as n goes to infinity of 1 over n, which is 0. So L is equal to 0. Great, except, okay, L being 0 is wonderful as long as my denominator series converges. But it doesn't. My denominator series is diverging. Right? I picked a divergent series here for B sub n. So that series right there is diverging. Boo. So this is actually case 4. Right? L is equal to 0, but B sub n diverges, which means the limit comparison test is inconclusive. Boo. Okay, well, it's weird, right? So you have to follow along with the specifics. So your denominator series converges, then it has to be 0. Your denominator series diverges, then it has to be infinity. But which one's numerator, which one's denominator, you kind of pick one. All right, so that did not work out either way. Like, that was a disaster. So let's try it a different way. All right, so let's try this particular one. Let's let a sub n be, I don't know, 1 over n squared, and b sub n be 1 over n cubed. Okay, so notice 1 over n cubed I know is a convergent p-series. As a matter of fact, I know both of these are convergent p-series. That's not the point, right? The point is I'm trying to show you a method here. So this is a convergent p-series. Right, just to make a note. All right. So the limit as n goes to infinity of a sub n over b sub n is the limit as n goes to infinity of 1 over n squared divided by 1 over n cubed. That's the limit as n goes to infinity of 1 over n squared times n cubed over 1, which is the limit as n goes to infinity of n, which is infinity. There's your L. Okay, limit is infinity. Great. That's going to be wonderful. The limit is infinity as long as my denominator series diverges. Boo. Boo. It's inconclusive again. Gosh darn it. I'm stuck with a case 5 again. My limit is infinity, but my denominator series is converging. All right, so this is case 5. Right, L was equal to infinity, but B sub n was converging. Right, it's a convergent p-series. So the limit comparison is inconclusive. You'd have to go do something else. Although in this particular problem, we know what these are. That's not the point. Right, I'm just showing how these how those other cases in the theorem work. We know what these are. So that's not what I'm trying to do. All right, so let's do it again. Let's go back. All right, so let's let a sub n be 1 over n cubed and b sub n be 1 over n squared. Again, I know that that is a convergent p-series. Right? Power is 2, 2 is greater than 1, it's convergent p-series. So then I can find the limit as n goes to infinity of a sub n over b sub n. That's the limit as n goes to infinity of 1 over n cubed divided by 1 over n squared, That's the limit as n goes to infinity of 1 over n cubed times n squared over 1, which is the limit as n goes to infinity of 1 over n. Because n squared, that's a cubed. Sorry, that was n cubed. Doesn't look like a power there. All right, so n squared over n cubed makes 1 over n, which is 0. We learned a long time ago in Calculus 1 that a constant over infinity is 0. There's my L. Oh, but this is going to work. If L is 0 and my denominator series converges, then this is great. This is case 2. Looking back here, that's case 2. If L is 0 and the denominator series converges, wonderful. Yay. So L is 0, the denominator series converges. So that implies that, I guess I don't need both of those words. I either need the arrow that says that implies, or I need so. So that implies that the A sub n series converges also. Yay. All right, so we've learned a couple things here that we want to pay special attention to. So number 1, A sub k and B sub k are arbitrary. Right? So it's possible to flip them, arbitrary to a certain extent. Right? But once you chose them, and you have to stick with it for the rest of the problem. So once I chose that to be my denominator, then I have to stick with it as my denominator. And you can see sometimes it'll work one way and not the other way, or vice versa. So to a certain extent. Right? So in other words, it doesn't establish which one they are at the beginning of the theorem. You can kind of pick whichever one you want. But then it matters which one was the denominator series down here. That's where it really counts, right? But the denominator series matters. For interpretation. Right? To interpret those results. Interpret results. To interpret results, sorry. Matters to interpret results. Right? In particular for case 3 and case 4, right? Or excuse me, cases 2 through 5, right? In case 2 through 5, the denominator will matter, right? Because here we saw it was infinity, but it wouldn't work because the denominator was convergent. Here we saw it was 0, right? So it matters for that bit of it, but the beginning selection of them is arbitrary. It doesn't matter which one you pick to be which one at the start. And number 2, L equals 0 and L equals infinity are tricky. Right? They can be inconclusive sometimes. Which is cases 4 and 5. They can yield results. Which is cases 2 and 3. And they can yield a result one way, but be inconclusive the other way, which is what happened to us on this one. And this last example right here, it was inconclusive on this side, but yielded a result on this side. So it can yield results, it can be inconclusive, or it could be a combination, depending on which one you chose to be the denominator one, right? And which one you chose to be the numerator. So even though I say it's arbitrary, if it doesn't work out and is inconclusive one way, then what you do is you try the other way. So if it's inconclusive, I'll just make a note. If inconclusive with A sub k, B sub k selection, flip them and try again. Which is what we did down here for this one. We had it be inconclusive with A sub n being this one and B sub n being this one, so we reversed it. We flipped them. We made it so that it was the other way, and then it worked out and yielded results. So that's another thing to note right here. So we have several notes down here.